So from there, one can say that RB is equal to 29.2 kilonewtons. RB is equal to 29.2 kilonewtons. So the next is to find RE. To find RE at the same part of the beam, DBE. To find RE, I take moment about B, total moment about B equal to 0. I have RE is 5 meters from B, so I have 5 RE plus 10. That's 10 times the distance from B is 3 times 3. 10 times 3 plus, because they are going the same direction with RE, the assumed direction of RE, they are going the same assumed direction of RE of 10 times 3, then plus 6, look at 6 here, 6 times the distance from B, which is 6, equal to 0. From here, I have RE is equal to minus 13.2 kilonewton. For the fact that that RE is minus 13.2 minus shows that that direction I choose of RE wasn't the direction. So RE is pointing down. That's the meaning of minus that we got. RE is pointing down. If you check them now to know whether you are right, if you put this RE pointing down here, if you check it to know whether we are right, you will see that 6 plus 10, which is 16, plus 13.2 will give you 29.2. That means RB is equal to all of them, total vertical distance. For total vertical forces is equal to 0. RB as a vertical distance up is equal to the whole vertical distance that is down. And that shows that the answer we got is correct. So the next thing now is to get bending moment, because we have gotten reaction in this reaction A, we have gotten reaction B, we've gotten reaction at E. What remains now is to get reaction at to deal with EC of the beam, That's what remains now. So when we get to that point, but now we have got the next thing is to get the bending moment. So let me now get bending moment. Bending moment, considering DBE. Bending moment, let me call here G. So bending moment at G. Bending moment at D will be 0 because there's no support there to sustain bending moment. So will be equal to 6 times the distance, which is 3. 6 times the distance is 3. That's from D to the middle. The whole distance is 6. So how is it? So which is 6 times 3, which is 18 kilonewton meter. That is the moment at G, and it is minus for that matter because of the way it's turning. The moment at B, moment at B will be minus 6 times the distance, which is 6. That is 6 times 6 minus 10 times the distance, which is 3. That is 30. This is 36 plus. That's 2 of them minus 36 minus 30, which is minus 66 kilonewton meter. That's the moment at B. The moment at B. That's the moment at B. So if I want the moment at the middle here, though I don't need the moment, I can get the moment at E if I want, but that's not the important thing now. So what I do now is, since I've gotten this moment, the next thing I need to get is to now deal with the part of the beam EC. The part of the beam EC is just like a cantilever, but there is the load that came from point A. That load is 13.2. So that point that is pointing down. So as it's pointing down from there in this cantilever, it will be pointing up, because it's pointing down from where it came from. The resistance from the cantilever will be up. That's shown here. Look at it here. So with this now, this is a cantilever, not a prop cantilever, not propped. So I don't need to look for reaction any longer. It is ordinary cantilever, not propped. If it's propped, I would have started looking for reaction, but it's not. It's ordinary cantilever. So what I do now is to get bending moment. So to get bending moment at point 12, at point, let's say this was, I give it G, let me give her H. At point H, to get moment there, M at H is equal to, the moment is equal to 13.2 times the distance, which is 1, is equal to 13.2 kilonewton meter. The moment at this point H, at the end, the moment at the end will be, the moment at the end, I'm trying to create space here so I can draw any moment diagram. The moment at H, I have here, I have the moment at H, the moment at H, there's the moment at the end, that is at C. I've gotten that of H. M at C will be equal to 13.2 times the distance, which is 4, 1 plus 3. That's the moment. This is going again, this is going the same way. So minus 12 times 3. That's the distance. That's 13.2 times 4, which is equal to 13.2. This is 0.8. This is 4 by 3 is 12. 4 by 3 is 12, which is 2. Take 1. 4 by 1 is 4. So 52. 52.8. 52.8. Then minus 36. 52.8 minus 36. That gives let's do this. 22. That's 16.8. That's 16.8 kilonewton meter. That's the moment at C. 0.8 kilonewton meter. So I've gotten the moments. I've gotten all the reactions, gotten the moments. So the next thing is to draw the bending moment diagram. So to draw the bending moment diagram. To draw the bending moment diagram, I sketch the beam. To draw the bending moment diagram, I sketch the beam. Bending moment diagram look this way. Here, it was a UDL. So the bending moment diagram becomes a curve. It becomes a curve and goes up to B. At this point, the moment at this point, that is the moment at point F. That's the moment at point F. I got the moment at point F to be equal to 6. The moment here is 6 kilonewton meter plus. It goes up at B. It tries to come down. From B, it moves down. And meets, because at the point of the hinge, that's the bending moment diagram. At this point, the moment at this point is moment at B. What did I get moment at B to be? Moment at B. I got moment at B to be 66. 66 kilonewton meter minus. Then here, that's the moment at, before, this is E here. Before EB, the moment between B and E. Then I got the moment at, that was 6. Then the moment, that was the moment I got at point C, the moment at C, which is 16.8 kilonewton meter. So that's the negative. That's the bending moment diagram. That's bending, this is positive. That's bending moment diagram. So for me to make the shear force diagram, I draw the same line. Reaction A is the first shear force, which in this case is 6. Reaction A. But that's the load starts to reduce the
the value of shear force, that is the shear force minus whatever the value of A is, it gets to, this is the hinge. It moves. That is the shear force diagram. Reaction A. That's 6. It gets it, the load reduces until when it gets to this point, the shear force from here, what was the reaction at D? What's the reaction at D? Reaction at D is also 6. Reaction at D, 6. So from there, it moves the same 6 until it meets 10 here. 10 that sends it down 4 places. Because it's no longer a UDL, it becomes a straight line. Gets to point B. Reaction B affects it. Reaction B, where is reaction B? Where is 29? It sends it up to, because it was 10, the other way was 10, to 19.2. So from there, no more, it continued that way until it meets 12. That brings it down to 7.2. This positive, this negative. This is 6, RA, 6. Continues to this point, 6, then here, this is 10. That's the whole of this, 10. This is 19, 20.2. Closes. So this is the shear force diagram. This is the shear force diagram. So I've been able to get the reactions, the bending moments, the shear forces, which are algebraic summation of the forces at every point. Shear force are the algebraic summation. What I mean by algebraic is that the summation considering the signs of the force, the sign that is positive or the one that is negative. Considering the solution was in consideration of the signs of the forces while we are adding or subtracting. While you are adding or subtracting. So that's how the shear force diagram. The value of shear force is, though if we differentiate bending moment, we get shear force, but what is really shear force is the summation of forces from where you started at every point. That is the shear force diagram. So we're able to get the reactions, get bending moment, get shear force. So that's the solution. With this, if this beam need to be, if you want to design this beam now, you can start designing because you have gotten the whole stresses. What name is a design. So this is a beam that is a continuous beam, but has 2 hinges. This is the solution. That's the end of this episode. Thank you very much.